Welcome to the 10th lecture in mechanics of materials. The last lecture we saw what an octahedral plane is. It was a plane that makes equal angle with the principal directions of the stress tensor. If n1, n2, n3 are the principal direction of the stress tensor, then the normal to the octahedral plane is given by 1 by root 3 n1 plus n2 plus n3. We saw that, and the normal stress on the octahedral plane is given by trace of sigma by 3, and the shear stress on the octahedral plane is also an invariant, which is given by this expression in here. Okay. We also took 2D plane stress state, and then we saw that if you write the spatial variation of the stresses to first order term in the Taylor series expansion, you can express the plane state of stress as this, wherein sigma xx, sigma xy, sigma yx and sigma yy act on two faces of the square, and the other two faces will have sigma xx plus dou sigma xx by dou x delta x, dou sigma xy plus dou sigma xy by dou y delta y, sigma xy by plus dou sigma yx by dou y delta y, dou sigma yy plus dou sigma yy plus dou y into delta y. And if B were to be the body force acting at the CG with components Bx and By, and acceleration were to be acting like this with components Ax and Ay in the chosen coordinate system, then we saw that the force equilibrium requires that divergence of sigma plus rho b equal to rho a, and the moment equilibrium requires sigma equal to sigma transpose. What we will do in this lecture is, first we will rederive the force equilibrium equations, and then the moment equilibrium equations. We will just formulate what is the governing equation, and then I will give the final result as what we obtained in the last lecture. Okay. And then we will move on to see what strain is. Okay. So, moving on, first we have to, for understanding what force equilibrium is, you have to state the Newton's second law, which says that, for which you have to define first the linear momentum, which will denote it by L, vector L. Linear momentum is defined as the mass times velocity, right. So, for us mass times velocity means we will have velocity plus rho times dV, where rho is density. So, that this term would essentially be mass. Density is mass per unit volume. So, if you multiply by volume, we will get the mass. Okay. So, this we will rewrite it as integral rho v dV v. Okay. Now, what does the Newton's second law state? It states that the rate of change of linear momentum is equal to the applied force in magnitude and direction. So, what is the applied force? Applied forces are two kinds of applied forces are there. Applied forces are two kinds, as we saw in the last class. One is what is called as the body force, and the other one is the contact force, right. So, if we denote this applied force by vector F would be integral B times rho dV plus T's of n dA, where what you are saying is this is body force per unit mass. Essentially, here we are considering body force as being due to gravitational forces alone. If it were to arise due to electromagnetic forces, then it will be per unit charge. So, since we are not considering charges in this course, or we are not interested in electromagnetic forces, we are considering the body force to be per unit mass. Okay. So, and this, as we saw before, denotes the mass. Okay. So, this gives the sum total of body forces acting on the body. This term is sum total of body forces on the body. Okay. Next, let us see what happens to this traction. I have a body. We saw in the traction that the boundary traction is also a cut surface, because the boundary is also a cut surface of the body. Okay. So, if a body, let us say a potato, has some distributed forces acting over the body, boundary of the body, okay, then the sum of all the contact forces is sum of all these forces that are acting on the body, right. So, basically it will be T sub n denotes the traction. If I integrate it over the area, I will get the net force that is acting on the boundary. This is force on the boundary, this force on the boundary. Okay. Because we define traction as distributed force acting per unit area. Okay. Distributed force acting over a cut surface or the boundary of the body, hence this is the net force acting on the boundary of the body, okay, that comes through contact means. Okay. Now, let us expand this. So, this will be equal to rho b dV plus integral sigma transpose n dA, because traction was, since T sub n was sigma transpose n as we saw before. Okay. Now, I want to convert this area integral into a volume integral. In order to be able to do that, I have to appeal to Gauss divergence theorem. Which says that integral sigma transpose n dA will be equal to integral divergence of sigma dV V if the region occupied by the body is a regular region and sigma is continuously differentiable in the interior of the body and continuous on the boundary of the body. Okay. Under these assumptions you can approximate or you can compute sigma transpose n dA as divergence of sigma dV. Okay. The important thing is you have to understand what a regular region means. Regular region, I will not go into definition of what a regular region is. You can look at the potential theory by Kellogg to understand what a regular region is. What we have to understand is any engineering domain is a regular region. Okay. So, regular region is not a restriction, but the fact that sigma has to be continuously differentiable in the interior of the body, it has to be continuous on the boundary of the body, is a limitation with which you have to apply the divergence theorem. Okay. In particular, what it means is, if sigma xx were to be given by x power half and the domain contains x equal to 0, then dou sigma xx by dou x is 1 by 2 x power half tends to infinity as x tends to 0, and hence one cannot use divergence theorem for these variations of sigma xx, or in other words what it means is, if you are looking at fracture mechanics, the crack tip has a stress blowing up to infinity. In such a case, the divergence theorem does not hold, and you can't solve the problem by writing the equilibrium equation of divergence of sigma plus rho b equal to rho a. You have to go to the integral equation, use the integral equation and then solve the problem. Okay. So, that is main thing that I want to stress here. So, to apply divergence theorem, the region has to be regular, sigma should be continuously differentiable in the interior and should be continuous on the boundary. Okay. Continuously differentiable at the interior and continuous at the boundary means, if I have the body to be defined, if I have sigma xs versus x from x0 to x1, what it means is I can't have such a variation, that is, it can't have different value at the boundary and some value different, two different values near the boundary, it has to be continuous. So, this is not allowed for sigma xs variation, that is what continuous at the boundary means. Okay. On the other hand, you can have variation like this, x0 to x1, on the other hand you can have a variation like this. Okay. So, you have to understand that we are using divergence theorem for simplifying the equilibrium equations which has certain assumptions in it, and you have to adhere to those assumptions. Okay. So, next let us move on. So, the force that we computed was integral rho b dv plus integrated over the boundary area T sub n dA. This can be written as integral v rho b dv plus integral sigma transpose n dA, which can be integrated to using the divergence theorem, can be written as plus divergence of sigma dv v. Okay. Here divergence of sigma, as explained in the previous lecture, stands for this vector dou sigma xx by dou x plus dou sigma yx by dou y plus dou sigma zx by dou z, dou sigma xy by dou x plus dou sigma yy by dou y plus dou sigma zy by dou z, dou sigma xz by dou x plus dou sigma yz by dou y plus dou sigma zz by dou z. Okay. This is what the divergence of sigma stands for, these three equations. So, force is this plus rho times Bx By, Bz is rho b plus this thing which is the force F. Okay. So, we computed the force, next we have to compute the rate of change of linear momentum. Okay, we have to compute dl by dt which is d by dt integral rho v dv, right. We saw that rho dv is mass times v. So, I can rewrite it as d by dt rho dv v plus integral rho dv dv by dt. In a chemically non-reactive system, rho dv, that is the mass of the system, does not change. So, this goes to 0. A chemically non-reactive system, the mass of the system does not change, hence this goes to 0. So, you are left with this equation, which is integral v rho a dv, where a is the rate of change of velocity, is nothing but acceleration. The rate of change of velocity. Okay. So, dl by dt now becomes integral v rho a dv. Okay. Now, what does the Newton's second law state? It states that F is nothing but dl by dt. So, next we will use that fact, F in magnitude and direction should be equal to dl by dt, which will imply that integral v divergence of sigma plus rho b dv must be equal to integral rho a dv, where a is the acceleration. Okay. So, now I can rewrite this equation as integral v divergence of sigma plus rho times b minus a dv equal to 0. Now, this integral equation has to hold for any subpart of the body also. It is not that it has to hold only for this body, it has to hold for a small cut inside that body also, it has to hold for this blue cut also, right. So, what it means is, it is not like sin x dx 0 to 2 pi becoming 0, it is the integrand has to be 0 for this equation has to hold, because this v is arbitrary. Okay. Since v is arbitrary, since domain is arbitrary, what we require is divergence of sigma plus rho b must be equal to rho a. This is the force equilibrium. Okay. So, this is the force equilibrium. Next we are going to look at moment equilibrium. Equilibrium. What does this state? For this I have to find what a angular momentum is. I will define angular momentum. Angular momentum is defined as, let us say A, this is integral x cross v rho dv. Okay. But this as usual is mass, okay. Where x is, if I have a body, Ex, Ey, Ez have a point in the body and x is this position vector of the point on the body. Okay. That is x, and this point has a velocity, this point has a velocity v. Okay. That point has a velocity v, and this is the definition of the angular momentum of a body integrated over the volume of the body. Okay. Now, according to the equilibrium equation, the rate of change of angular momentum must be equal to the net force, net moment or torque that is applied on the body. Okay. So, we have to find the net torque on the body, net torque or moment applied. Okay. Let us note that by m is going to be equal to, if I have distributed force acting over here, contact force, okay, that torque is going to be again integral x cross T's of n dA, where this is the force, this is lever arm times the force, because moment is r cross f. Okay. Since moment is r cross f, that will be the moment that is applied on the body, okay, plus integral x cross rho b dV. This moment is due to contact force and this moment is due to body force. Okay. Now, in addition to this, there can be body couples if there are charged particles in the body. In addition to this, there can be body couples if there are charged particles in the body, which we are ignoring, since we are not interested in electrically active or magnetically active materials. We are ignoring the presence of body couples or body moments. Okay. Under that assumption, let me state that assumption here, ignoring body couples or moments, okay, m is given by this expression, m is integral a x cross T's of n dA plus x cross rho b dV. Okay. Under this assumption, m is z. Now, according to the theorem, according to the approximation law, rate of change of angular momentum must be equal to the applied moment in magnitude and direction. Okay. What does this state is? dA by dt must be equal to m. This will imply d by dt integral x cross rho v dV integrated over the volume must be equal to integral x cross T's of n dA plus x cross rhos of B dV. Okay. Now, I am not going to go into a detailed derivation to show the final result. You can look up advanced solid mechanics NPTEL notes to see web course to see how we get the final result now from this expression. It involves a lot of tensor calculus and tensor algebra, which I do not want to get in this introductory course. Okay. So, this is a statement of moment balance. So, under this condition you will find that sigma must be equal to sigma transpose, okay. Sigma must be equal to sigma transpose when there are no body couples, okay. So, basically what this tells you is the stress tensor is a symmetric tensor, okay. This implies stress is a symmetric tensor, okay. That is sigma xy must be equal to sigma yx, sigma xz must be equal to sigma zx, sigma yz must be equal to sigma zy, okay. Moment equilibrium is a force equilibrium, is a vector equation, and hence you have 3 components of that. The 3 components will be these essentially, okay. So, what you have seen till now is how to get the force equilibrium and the moment equilibrium systematically from the Newton's second law. We saw that the force equilibrium results in an equation of the form divergence of sigma plus rho b equal to rho a when the stress field is continuously differentiable in the interior of the body and it is continuous in the boundary of the body, which means there is no discontinuity between the boundary and the interior, and it should be differentiable in the interior, which means the stress cannot blow up in the interior of the body, okay. The next condition is the body has to be what is called occupy a region what is called as a regular region, okay. We said that all engineering domains are regular, so we are not concerned about the precise definition of what regular region means, but divergence of sigma plus rho b equal to rho a holds only when the stress is a continuously differentiable field in the interior of the body. Similarly, the stress will be a symmetric tensor only when there are no body couples or we are not looking at electrically or magnetically active materials, okay, which is what we are interested in this course, okay. So, till now we have seen what the stress is, what force is, the equation that connects the stress and the force, the equilibrium equations, okay.